In this video, we're going to be solving a rotations FRQ. A person is standing on a horizontal disc-shaped platform that can rotate with negligible friction about an axis about the disc center. Initially, as shown in figure 1, the person is standing at the edge of the center of the disc as the disc rotates in the counterclockwise direction with a constant angular speed omega initial. Then, as shown in figure 2, the person walks to the edge of the rotating disc. When the person reaches the edge, the disc rotates counterclockwise with the speed of omega f. Counterclockwise. When the mass of the person is mp and the mass and the radius of the disk are md and r respectively. Indicate whether omega f is greater than, less than, or equal to omega initial. So what we have is that there is no external torque acting on the system because there's negligible friction, so there's no external torque. That means that you have conservation of angular momentum. So that means that the system, so our system right now, our system is equal to the person plus the disc, and the only thing that's changing is this person and their position on the disc. So in this system that includes this person and the disc, there's no external forces acting. So that's why conservation of angular momentum is conserved. And we can write our angular momentum as L is equal to I omega and keep that. So what we have is that when the person walks from the center to the edge, the distance from the axis increases. So they are moving outwards. The distance from the axis, which is the center that it goes through, it's increasing. And we see that will increase the rotational inertia of the system because I is equal to mr squared, which is the mass. The mass is going to stay the same here. And the radius is going to change though. This is going to change because the person is moving further away. The radius is measured from the distance that the person is at to the center of where the axis of rotation is. So since the angular momentum in our system is going to stay constant, since our angular momentum, this is going to stay constant. It's constant. And we know that I times omega is going to consist of the same angular momentum. So what this means is that because the angular momentum, it must stay constant, an increase in rotational inertia is going to mean that angular momentum is going to decrease. Since if you have 2 times 4 equals 8, and you have 4 times something, you have to reduce your second number to 2 to still make it 8, as an example. So we would choose this option. This is the same principle as a figure skater extending their arms and slowing down. The rotational inertia of a disk about its center is 1/2 md r squared. Derive an expression for omega f in terms of omega initial, mp, md, r, and physical constants as appropriate. So we're going to write our conservation of angular momentum principle. So that's initial is equal to final. So I initial omega initial is equal to I final omega final. Now, initial rotational inertia, we know that initially our person stands at the center. And if the person is standing at the center, we also can talk about how this is going to be a point mass. So at this moment, the radius is going to equal to 0. And I is equal to 1/2 mr squared. So that means that you would have 1/2 m times 0 squared, which would be 0. Therefore, it would contribute 0 rotational inertia. So in our problem, what we have is I of the disk is equal to 1/2 m mass of the disk radius squared. So I initial is equal to 1/2 mdr squared. Now we have to find our final rotational inertia. So this is when you're at the edge. So finally, our final position is going to be when you are having the person that reaches the edge. Person reaches edge. So when this happens, the person is going to behave like a point mass, but this time with a radius that is not equal to 0. It's going to equal to r. So I is equal to 1/2 mr squared. General form, so that's 1/2 of the, so I of the person is equal to mass of the person times radius squared. So for your total final, IF, you're going to have both the rotational inertia of the disk, which is 1/2 mdr squared plus mpr squared. So now you can set these equal to each other with conservation. So you have our principal up there. We'll continue that over here. So we have 1/2 mdr squared omega initial, which was our I, is equal to 1/2 mdr squared plus mpr squared. So that is equal to omega f. So now after this, you need to solve for omega f. So if you divide both sides by r squared here, and you're going to be able to cancel that out, you're going to have 1/2 md omega initial is equal to 1/2 md plus mp omega f. For omega f, you would get 1/2 md divided by 1/2 md plus mp times omega initial. So this would be your final expression, or you could also write this as md over md plus 2mp times omega initial, because you could just cancel out that 1/2, and then instead you would just write a 2 coefficient for that mp in the denominator. This is a subscript, by the way. So we can talk about our part C now. Indicate whether the equation derived in part B is consistent with the claim you selected in part A and justify your answer. So our equation was omega f is equal to 1/2 md, and that's divided by 1/2 md plus mp times omega initial. So what we can see here is that our numerator is smaller than our denominator. So what that means is, for example, you have 1/4. That means your fraction is going to be less than 1. Fraction is going to be less than 1. So that means that omega f is going to be less than omega initial. And we can write that this agrees with the claim in part A, that angular speed is going to decrease. You can say angular speed decreases when your person moves outwards. When person moves outward, because your rotational inertia increases while your angular momentum stays constant. Angular momentum stays constant.